And welcome to this webinar on macroscopic ray-based modeling of scattering from reconfigurable intelligent surfaces. I am Vittorio Degli Esposti, and the webinar will be also taught after myself by my colleague Enrico Vitucci, and we are both from the Department of Electrical Engineering of the University of Bologna. So the first part of the webinar, the blue part in this outline, will be taught by myself with some basic theory and some general characteristics of the model we propose. The rest of the seminar will be taught by my colleague Enrico. So let's start with some basic theory regarding some geometrical optics concepts. First of all, what is a wavefront? We know that in free space, the field, or better, the far field generated by a source can be written through this equation. So the field in a spherical coordinate system can be written as a vector amplitude, which depends only on the angular coordinates, and then multiplied by a propagation factor, which includes at the numerator the phase factor with the rotation of the phase due to the propagation, to the path the wave is propagating through. And then we have the distance at the denominator that attenuates the field. If we consider only one component of the field, for example, the x component, then we have a complex factor and the propagation factor. We can factor out the modulus of the complex amplitude and put together the phase. So the wavefront is a locus where the field has constant phase. So we must pose argument of E0x minus beta r with beta phase constant equal to a given arbitrary constant. If we are in the far field, r is large, and if the argument of E0x is limited and can be neglected with respect to beta r, then we get, of course, the equation of a spherical surface. So we say the wavefront in this case is quasi-spherical. That's why we call this a spherical wave field. But in general, wavefronts can have an arbitrary shape, especially in presence of metasurfaces. And the field must then be written in this form, which my colleague Enrico later on will use. So the field as a function of the position vector r is equal to a vector amplitude, also function of r, multiplied by a phase factor where distance appears inside a nonlinear function called iconal. And in this case, the wavefront can have many different shapes, not only spherical. What is a ray? So given a propagating wave, every line, every curve that is everywhere perpendicular to the wavefront is called electromagnetic ray, sorry. So a ray is orthogonal to the wavefront and represents basically the path of the wavefront. So there is a mutual identification between ray and wave that propagates in a given direction. We also assume that the ray carries a field. The field of the wave in the intersection point between the ray and the wavefront that we consider. For example, if we have a source in far field with spherical wavefronts, rays are lines departing from the phase center of the antenna and propagating in the radial direction. Of course, given that the source is not necessarily omnidirectional or not to mention isotropic, so the intensity of radiation is different in different directions, and therefore different rays carry different field intensities. For example, if this is the axis of the antenna, this ray will be stronger in terms of field with respect to the others. In free space, rays are straight line, are rectilinear, and wavefronts are spherical. In presence of obstacles, like in this case, where we have, for example, terrain, waves reflect and rays change direction. And therefore, in presence of obstacles, they are piecewise rectilinear, and wavefronts can be of various shapes, as we will see later. In non-homogeneous media, rays can have a curved shape, but we will not address this phenomenon in this webinar. What is a ray tube? A ray tube, or tube of flux, is a closed tube whose lateral surface is formed by rays and the bases by two wavefront sections. So we have rays that are not necessarily parallel, as we have seen. We have a tube, and then we have two cross sections of the tube, the sigma 1, the sigma 2, which are not equal, and this is a ray tube. If the ray tube is thin, we can assume a constant field over the cross-section, and therefore we can represent the whole tube with its central ray and the field of this central ray. And this will be used later on in ray launching models. Assuming constant field over the cross-section, for power flux conservation, we can derive the intensity law of geometrical optics that states that field intensity is inversely proportional to the square root of ray tube cross-section. So the narrower the ray tube and the greater the intensity, which is the modulus of the field. And therefore, this equation applies. This ratio is also called spreading factor. And we can write the equation in this way. So the intensity of the field at the second cross-section at a given distance from the first one can be written as the intensity at the first one multiplied by the spreading factor. The spreading factor depends, of course, on this distance along the ray, and is a sort of path gain in terms of field. It is usually lower than 1 if the rays spread in space. If we also consider phase and polarization, we can write the field transformation equation in this way. So the overall phasor of the field at the second cross-section is equal to the product of the field at the starting cross-section, multiplied by the spreading factor and by a proper phase factor. But in general, ray tubes and wavefronts are astigmatic, which means that they are not spherical or plane. The wavefront has two curvatures into two principal curvature directions, which are orthogonal to each other. And for each curvature, we have a radius of curvature, rho 1 and rho 2, or rho 1 plus s and rho 2 plus s for the curvature at the second surface. In this case, it can be shown that the spreading factor is a function of the radii of curvature, rho 1 and rho 2, and of the excess distance. So this is the most general expression of locally astigmatic ray tube. And it boils down to well-known cases. For example, if the two radii of curvature are the same, we get a spherical case, otherwise cylindrical or plane wave, where when the two radii tend to the infinite and the spreading factor is 1. So a few words on ray tracing before applying this theory to reconfigurable intelligent surfaces, or meta surfaces, as you want to call them. So what is ray tracing? The term ray tracing defines a class of methods or models to describe the electromagnetic fields using a set of rays. Since at the observation point we have multipath in general, multiple rays must be found by the ray tracing algorithm. So ray tracing finds some of the rays that propagate between two or more points through free space propagation and interactions with obstacles, in particular canonical obstacles with flat surfaces and straight edges. The geometry and the field of the ray must satisfy geometrical optics. The interactions, reflections, diffraction, scatterings, are generically called events or bounces, and usually the algorithm finds all the rays that undergo up to a preset number of bounces, NB. So ray tracing is widely recognized as the most efficient deterministic radio propagation approach that can achieve a complete characterization of propagation and therefore of the radio channel, including radio coverage, but also time dispersion, angle dispersion, etc. Performance depends on the accuracy of environment description, of course, but also on NB, the number of bounces. The greater NB, the larger the number of rays, the better the accuracy. Usually 3 or 4 is enough for outdoor prediction, while 2 or 3 for indoor. Unfortunately, computation time grows more than linearly with NB, and therefore a trade-off must be found so that the prediction error is low enough, but CPU time is not too great. Anyway, computation time represents a problem, but it's orders of magnitude smaller, shorter, compared to electromagnetic simulation method. And therefore, ray tracing is one of the preferred methods for channel characterization. Since bounces over obstacles are considered, then the field must be computed in presence of interactions. So in this case, we apply a similar a similar field transformation equation as the one we have just seen, but each time there is a bounce, an interaction, we have to pre-multiply the field by the proper interaction matrix that embeds the interaction coefficients, such as reflection coefficients, diffraction coefficients, etc. So we have the field at the starting point, at the reference point after the transmitter, multiplied by the proper spreading factor that depends on the history of the bounces, multiplied by the phase factor, but also pre-multiplied by the interaction matrices. So it's quite simple most of the computation time in ray tracing depends on the, let's say, geometric ray tracing phase, not on the field computation, which is a simple analytical expression. So the question we will try to answer later on in this webinar is, can we use ray models also when obstacles are RIS or metasurfaces? In that case, what reflection diffraction coefficients and spreading factors shall we use? So now we see, we compare two possible implementation of ray tracing, image ray tracing and ray launching. In image ray tracing, IRT, rays are searched and traced for specific transmitter and receiver position. So the position of the terminals are known a priori before tracing the ray, and only the actual rays propagating between TX and RX are found. For example, with one reflection, two reflection, or two bounces, including reflection and diffraction in this typical, environment, are shown in these pictures. As you can see, the number of rays can become very large as the number of bounces considered increases. In order to find the rays, the image method is applied. So basically, we find the mirror image of the transmitter. We intersect the mirror image with the receiver, and we find the reflection point, also called critical point. And then we draw the ray, the reflected ray, according to this image method. The procedure can be iterated for multiple reflections, and a similar procedure can be applied for diffraction on edges. What's the difference of ray launching versus image ray tracing? In ray launching, rays are launched regardless of the receiver point. So starting from the source, we launch rays, or better, ray tubes, because in this case, rays represents a whole ray tube around them. So starting from the transmitter, we launch rays with a given angular step in all the directions, and then we follow the rays, and a posteriori we check whether those rays hit a given receiving point, a given pixel that we want to consider. So in this case, the central ray represents a whole ray tube, and the field is considered constant on a ray tube cross-section. So we have a limit on resolution in ray launching, which was not present in image ray tracing. On the other hand, a ray tube covers a finite volume in one shot. And therefore, when we launch one ray, then we get the field all over the ray tube. And therefore, ray launching is faster than ray tracing for coverage prediction over areas or volume. For example, considering even free space propagation without any bounces, if we have 4 receiving point pixels that fall within the same ray tube, in only one shot, we compute the field over all those pixels. It is enough to determine whether the pixels fall within this ray tube, but then the field is the same over the cross-section, and the field can be transformed along the ray tube very easily in analytical form using the field transformation equation we have seen. While in image ray tracing, we need to address specifically each pixel multiple times. And therefore, computation time is higher. In ray launching, each time a ray hits the edge of an obstacle, then we have to split the rays again. So the diffracted rays are relaunched on the Keller cone, starting from the edge, with a similar angular separation as from the source. There are more efficient relaunching implementation that instead of launching rays in all the direction, launch rays only toward the obstacles. So the obstacles are basically discretized. That's why we talk about discrete ray launching. And then the rays are launched toward each one of those surface elements, those visible surface elements. And this algorithm can be iterated for multiple bounces. So we can pre-compute the visibility relationship between different, surface elements, and then launch rays at each step only toward visible tiles. You can find some details about this algorithm in this paper, but we don't have time to delve into the details. Let's now come to ray tracing and meta surfaces. Why does image ray tracing use the transmitter mirror image? Because the mirror image is the center of the reflected wavefront from a given surface, and therefore it is the origin of the reflected rays. The mirror image is similar to what we have with a mirror and the image of a face with respect to the mirror. But with a metasurface, there is no clear origin of the reflected rays because the reflected wavefront can have an arbitrary shape. There can be multiple images. And those images and the critical points on the surface can still be identified with some kind of iterative procedure, but the procedure is computationally intensive. So this is the case similar to a curved mirror where we get multiple images of the face, right? So image ray tracing can be slow for meta surfaces or reconfigurable intelligent surfaces. Therefore, in our opinion, the best algorithm for reconfigurable intelligent surfaces is discrete ray launching. So basically, we somehow discretize the surface, the meta surface, into spots, into surface elements. Then we launch rays toward each one of them, and the ray is deflected according to the physical characteristics and the configuration of the metasurface at each spot. No need for iterative critical point search and easy parallelization. So in the next slides, we will see how metasurfaces, or better, reconfigurable intelligent surfaces, can be modeled in order to apply ray launching on them. Only reflecting surfaces will be considered for simplicity, although the method can also be applied to other kinds of surfaces. So some terminology. There are many different technologies and applications. Generally, we speak of nearly passive, low-cost panels with some active control logic. As you know, RIS are conceived to reflect the energy toward a given desired direction instead of the usual specular direction as usual surfaces, or to somehow manipulate the field. For example, focus the energy toward the receiving point, change the characteristics of the field, etc. They can be reflective or transmissive. They can also be transparent and re-radiate the field on the opposite direction with respect to the surface. There are large-scale applications, such as RIS-assisted communication, large RIS or smart skins to improve coverage. There are small-scale applications, for example, cloaking metasurfaces and metadomes for antennas, signal processing devices, etc., where a metasurface is used to wrap a very simple source and then change the radiation pattern in a dynamical way. And there are basically two main technologies, even though this definition is not universally, let's say, recognized. The first technology is the real metasurface technology with electrically small surface element printed on a substrate, which are also called meta-atoms. This is cheap technology, but reconfigurability is difficult or somehow limited, and there are parasitic radiation modes. So the surface can radiate multiple modes, not only the desired wave we intend to the RIS to radiate. Otherwise, there is an alternative, more traditional technology, which is a reflect array or transmit array technology with larger unit cells. Typically, the spacing is half lambda. In this case, given the larger size, reconfigurability is easier, but the cost is higher. And also in this case, there are side lobes. So not only one radiation direction, but multiple, let's say, spurious radiation modes. And also, most reconfigurable realizations suffer from phase error and phase discretization, and therefore there are undesired errors and diffuse scattering that we have to take into account. So models can be microscopic. So in this case, we have electromagnetic or microwave network simulation methods based on the RIS microstructure. And these models are necessary for the design, for the detailed analysis of the behavior of such surfaces. However, these models are computationally very heavy. Otherwise, we can have so-called macroscopic modeling, where the radiated field is found based on the simplified parametric description of the RIS, bypassing its actual technology details and yet keeping physical consistency. So such models are simpler and more suitable for efficient simulation of RIS-assisted systems. Unfortunately, current models are either complex microscopic models, such as electromagnetic simulation, or idealized simplified models, such as, for example, scattering matrix model, where each element is thought as independent of each other and represented with a simple complex weight. Neglecting many parasitic effects and problems. So is it possible to have something in the middle? So something that's simple enough for suitable efficient simulation and yet electromagnetic consistent? So that's what we have tried to do. And the base is to start from homogenization. So most metasurfaces can be homogenized and described with a spatial modulation coefficient, which is basically a variable reflection coefficient that directly addresses the corresponding wave and field transformation the RIS is conceived to apply. and this is done for each re-radiation mode if the metasurface re-radiates more than one mode. So you can find the basics of this representation in this paper we published a few years ago. And we start from the spatial modulation coefficient to directly calculate the wave transformation. Of course, one could criticize this approach because what is the relationship between the homogenized RIS and the real RIS or RIS? Because real RIS are, for example, arrays with discrete elements, etc. So we need to somehow find a bridge between the discrete RIS and the homogenized RIS. For example, doing some kind of smoothing of the phase weights of the discrete one to get the homogenized RIS. But most of the time, especially for electrically small atoms, metasurfaces, the design starts right from a given target spatial modulation coefficient, and then the synthesis is done starting from this to derive the actual microstructure of the metasurface. And therefore, you know, simulation starting from the SMC is more efficient. Otherwise, one needs to start from the microscopic structure, the particular configuration, carry out a complex electromagnetic simulation, and then calculate the field transformation. So, of course, this gamma needs to be determined based on simulation, measurements, or theory for a given RIS. So the spatial modulation coefficient includes several parameters. For example, the phase modulation parameters, key M, which also determines the so-called phase gradient of the metasurface, but also an amplitude coefficient of the considered re-radiation mode that determines the amplitude of the mode. Also an additional normalized amplitude modulation coefficient that's useful to describe non-local effects over the metasurface, and a polarization matrix for polarization description. So at the end, the spatial modulation coefficient is, if you look at this last expression, has an amplitude, phase, and the polarization matrix, and each one of these is defined using a number of parameters. For example, the radiation amplitude. These are different from this is the attenuation coefficient due to diffuse scattering, for example, and then the phase parameter, etc. So the radiated field can be computed using the field transformation equation we have seen before. So the field at a given distance from the metasurface can be computed starting from the field, the incident field, multiplying the incident field by the proper spreading factor, the phase factor, and pre-multiplying it by the spatial modulation coefficient that in general is a matrix or a dyadic, as most people say. Of course, the parameters of the SMC and the spreading factor needs to be found, and they are not trivial. So that's what my colleague Enrico will deal with in the second part of the webinar. The parameters in particular, the amplitude parameters of the radiation modes must satisfy a power balance. So the power balance we developed is based on a generalization of the effective roughness surface scattering model power balance, which you can find in this paper. So the original power balance in the effective gruffness model stated that the incident power on a given surface element must be balanced by the reflected power, the diffuse scattered power, and the dissipated power inside the surface, or inside the material. But now we also have the re-radiated power, the anomalous radiation. Therefore, we have one additional term that depends on the radiation coefficient. And we also have a scattering coefficient because we have to take into account that due to inaccuracies in the realization or phase errors, quite a lot of diffuse scattering can be generated by the metal surface at the expense of the desired re-radiation mode. And therefore, we need to reduce the amplitude of the radiation mode. If we consider multiple modes, then we can include the specular reflection into those modes, and we can simply say that the incident power is balanced by the re-radiation power, scattering power, and dissipation. And so re-radiation and scattering depend on the sum of all the radiation modes, so that the parameters must satisfy a power balance equation. So the power balance can also be generalized to transmissive or bilateral RIS, not considered here, and it enforces physical soundness and determines the relative amplitude of the different modes. Of course, some of these parameters in this equation must be defined through theory or measurement on a given sample, and the others can be found using power balance, because we need the waves to satisfy power balance. We cannot accept any creation or destruction of power in the metal surface. So the scheme of the ray-based model we developed and we would like to present in the rest of this webinar is the following. So based on the definition of the parameters and of power balance, the re-radiated ray field amplitude is defined. Then, on the basis of the phase gradient of the SMC, the radiated ray direction is found. And finally, based on further derivatives of the phase gradient that define basically the curvature of the local curvature of the wavefront, the re-radiated ray spreading factor is calculated. So the rest of this seminar will show more in detail how to perform steps 2 and 3 for a reflecting RIS as reported in this relatively new paper. So finally, we are trying to propose a macroscopic and yet electromagnetically consistent ray-based model for RIS. And my colleague Enrico is going to present now the rest of this webinar. Thank you very much for your attention.
Thank you, Vittorio. We now continue the webinar with the presentation of a ray model for reconfigurable intelligent surfaces that we recently developed. First of all, I want to recall again some basic concept of geometrical optics. Vittorio has already told you about rays. We can also define the geometrical optics field, which is given by these two equations for the electric field and magnetic field. In these expressions, we have the so-called eikonal function, which is related to the phase of the electromagnetic wave and in the end to the shape of the wavefront. Also, the geometrical optics theory is strictly related with the locally plane transverse electromagnetic wave assumption. In fact, if we substitute these two equations into the Maxwell equations, we get these expressions. And the meaning is that we have EH fields, which are on the orthogonal plane with respect to the ray direction. And the ray direction is given by the gradient of the eikonal or phase function. It is quite well known that in homogeneous media like free space, the rays are rectilinear, but this is not true in general for other media. Another important concept that I want to recall is the curvature matrix. Vittorio already told you that in general the shape of electromagnetic wavefront is astigmatic. So we can define this astigmatic ray tube where we have two different curvatures, ρ1 and ρ2. And we can also define these two unit vectors, x1 and x2, which are called the principal curvature directions. A compact way to express the concept of principal curvatures and principal curvature directions is using the so-called curvature matrix. The curvature matrix is the Hessian matrix of the eikonal functions, so it contains the second-order derivatives of the phase of the considered wave, and it can be expressed following way as a matrix whose eigenvalues are the principal curvatures and whose eigenvectors are the principal curvature directions. So the eigenvalues of this matrix are the reciprocals of the curvature radii ρ1 and ρ2 plus s, which is the local coordinate along the ray. So we know that when a wave propagates, the length of this curvature ρ1 and ρ2 increase by this quantity s, which is the excess coordinate along the ray with respect to a reference point on the ray S0 equal to 0, where the values of the curvatures are the reciprocal of ρ1 and ρ2. This matrix is a rank 2 matrix by definition, and in general, it will be a 3 by 3 matrix. And obviously, in the case we define the matrix according to a ray-fixed reference system, so if I make use of these orthogonal bases, x1, x2, and s, this matrix is diagonalized, so it can be expressed in this form. One more property I want to highlight is that by definition, the product of the Q matrix by the S unit vector, which indicates the direction of the ray, is equal to 0. And finally, I want to recall that since the non-zero eigenvalues of this matrix are the reciprocal of the curvature radii of the wave, we can express the spreading factor of the electromagnetic wave according to this form. So in the end, the electric field along a ray, it can be expressed in this way as a product of the electric field on a reference point having coordinate s equal to 0 multiplied by the square root of this ratio, which is the ratio of the pseudo-determinant of the Q matrix at a point on the ray with local coordinate s and the pseudo-determinant of the same matrix at the reference point s equal to 0. And also we need to multiply this expression by the phase factor. And this is the results, the final result of this operation, of this computation. We get again the spreading factor in the form that it was already presented earlier by Vittorio. Okay, so this pseudo-determinant is simply the product of the non-zero eigenvalues of the matrix, because this matrix is always rank 2, so we have to make the product of this eigenvalue and this eigenvalue. And this must be done at the reference point s equal to 0 and at the considered point, at the considered value of the local coordinate along the ray, to get the value of the electric field at the considered point. Okay, after this quick recall, now I go ahead with the presentation of the ray model. First of all, there are some basic assumptions that I want to summarize here. The first assumption is that we rely on the concept of homogenized surface, and we assume that the properties of this surface vary slowly at the wavelength scale. So we have basically a modulated RIS, but this modulation is slow with respect to the variation of the length of the wavelength. The next assumption is that in general, the RIS will radiate a field which can be composed as a set, as a discrete set of different radiation modes. This is the typical case of locally periodic metasurfaces, which generate Floquet's modes. Also, another important assumption is that with this ray model, we are able to compute the radiated far field and near field, in particular radiative near field, for any incident wave on the RIS. But in this computation, we do some approximation. So at the moment, we neglect in the model the effect of evanescent modes, like surface waves, and also vertex diffraction. We only consider diffraction by the edges of the RIS and not by the vertices. The method we propose to compute the radiated field can be applied to any propagating mode of the RIS. In case we have, for example, 3, 4 propagating modes, we have to iterate the method that I will present now for each of the propagating modes. And the method consists in 3 stages, which I summarize here. The first stage is the computation of the radiation angle at a given point, at a given point or tile of the surface. The next step is the computation of the radiated field on the RIS surface. And the final step, last but not least step, is the computation of the spreading factor. With this spreading factor, we are able to compute the way the radiated wave attenuates along a given ray. So it's very important. Let's start with the radiation direction. First of all, we divide the RIS into tiles. And for each tiles, we can rely on the locally plane wave assumption. Okay, we can always choose the size of the tile so that whatever is the distance of the transmitter, for example, whatever is the shape of the incident wavefront, it can be considered locally plane on the tile. And one more thing I want to highlight is that this point of view is suitable for a forward ray model approach. So it's basically suitable for a ray launching approach. So we launch rays or ray tube along towards each tile of the along the surface, and for each of them we compute the radiation direction, which means that the radiated ray tube, and finally we compute the radiated field along each of the different ray tubes. In this simple example, we can see that a representation of two different types of RIS, the anomalous reflector and the focusing lens. In the latter case, we can see that all the ray tubes are converging into the focus, which is the point, the spot where we want to focalize all the power radiated by the RIS. The next step, as I told you before, is the computation of the radiated field. In particular, in this case, it's the reflected field on each tile of the surface. Each tile can be expressed by this R prime vector, which is the position vector of the generic tile on the surface. And then we will have the incident electric field, which is the field of the locally plane wave incident of the tile. And we express the radiated field on the tile by multiplying this incident field by this gamma coefficient, which is called the spatial modulation coefficient. This coefficient in general is a matrix or a dyadic and not simply a scalar coefficient. In this way, we are able also to address the case of RIS, which is able to transform the polarization of the incident wave into a different polarization. So in the end, this coefficient is composed by three factors. The first factor is this phase, exponential complex exponential, where we have the phase imposed by the RIS on the generic tile. And as I said before, this phase varies at the scale of the wavelengths. Then we have the amplitude modulation. In some cases, it might not be present, but in general, this spatial amplitude modulation might be needed in some particular cases, for example, to take into account the fact that we have some reduction of the radiated power due to inefficiencies of the RIS, or some effects caused by diffuse scattering, or again, non-local effects. So, for example, power exchanges between different tile of the surface. And with this amplitude factor, we are able to take into account all these effects. And the last factor, as I said before, is this dyadic Rm, which can change the polarization of the incident field into another polarization. The last step of the model is the computation of the spreading factor. This is very important because, in general, a modulated RIS modifies the shape of the incident waveform into a different shape. Okay? So this means that we have a different attenuation law along the ray after the radiation by the RIS. And we need to know the spreading factor, the proper spreading factor, to be applied to each of the radiated rays. This is very similar to what happens, for example, in the case of incident wave on a curved surface. So in the case we have a stigmatic wave incident on a curved surface, the reflected wave will be still astigmatic, but the local principal curvature will change. So we will have a reflected curvature radius ρ1, which will be different from the original curvature radius ρ1 of the incident wave, and the same applies to the second curvature ρ2. So the shape of the curved shape of the surface, even in the case of regular surfaces, in general changes the shape of the waveform, and in the end the spreading factor, which is the following one after reflection. This is something very similar to what happens in the case of a RIS. So even in the case the RIS is not curved, but it's a flat surface, due to the spatial modulation, which is imposed by the RIS, the result is that, again, similarly to the case of a regular curved surface, the spreading factor is modified by the RIS. Okay, after we have explained all the steps of the model, now I go a little bit more into the detail of the computation of the radiated field. First of all, we must substitute the expression of the geometrical optics incident and radiated field into this relation, which is the one imposed by the spatial modulation of the RIS. We simply substitute the geometrical optics expression of the fields, and we get this equation, which can be split into two parts. The first part is the one related to the amplitude and polarization of the reflected field on the surface, on the generic tile, while the second part is an equation which defines this phase matching condition that must be satisfied on the RIS surface. So it means that the phase of the reflected field of on the tile is equal to the phase of the incident field on the tile minus this factor, which is related to the phase modulation Km imposed by the RIS. Okay, this is the starting point of our model. So let's now continue with this second equation. First of all, we can express the incident and reflected phases of the incident and radiated wave by using the Taylor's series expansion about a reference point, R0 prime on the surface. And we get these two expressions, 5 and 6, where we can see the zero order, first order, and second order terms. It is worth noticing that in the first order term, we have the gradient of the phase, which is in the end the direction, local direction of the ray, S, while in the second order term of this Taylor series expansion, we have the Hessian matrix of the phase, which is in practice what we called before earlier the curvature matrix Q. The two are the same. So the curvature matrix Q is the Hessian matrix of the eikonal function, which is the phase function of the geometrical optics field. These two expressions are basically the same for the incident and radiated field, and also we can define the Taylor series expansion for the phase modulation Km imposed by the RIS. Now we simply substitute this expression into the phase matching expression I presented before, and then we can separate the zero order, first order and second order terms, and we get these three different relations. The first relation is trivial. It is simply the phase matching of the waves and the phase of the RIS at the reference point R0 primes, while the other two are very important. In particular, the first order equation, balance equation, gives you the tangent component of the radiation locally radiation direction, locally radiated wave, while the last one on the right gives you this expression which relates the curvature matrix of the reflected wave to the curvature matrix of the incident wave and to the second order derivative of the phase modulation imposed by the RIS, which is this nabla Km. It is the Esham matrix of the phase profile imposed by the RIS Km. Okay, let's now go into the details of these two expressions. Let's start with number 9. Number 9 can be rewritten in the following form, where I have introduced this tangent projection operator, P. So this equation means that the tangent projection of the radiation direction SR, reflection direction SR, is equal to the tangent projection of the incident ray direction minus this expression, the gradient of the phase imposed by the RIS divided by the wave number. Okay? This expression is composed by two parts. The first part, P multiplied by SI, is in practice what we call the incident phase gradient. Okay, this incidence phase gradient, nabla Ki, is then summed in this expression to the phase gradient imposed by the RIS. So we can define this nabla Ki as the total phase gradient. So it's the summation of the incident phase gradient related to the ray inclination and the phase gradient nabla Km imposed by the metasurface or RIS. And if we rewrite the previous expression according to this assumption, we have immediately this result. The tangent component of the reflection direction SR is equal to the total phase gradient, to the opposite of the total phase gradient divided by the wave number. So this means that anomalous reflection direction SR takes place according to this total phase gradient, and we will have a radiation plane, which is the blue one in this figure, which is parallel to this total phase gradient direction on the RIS plane. Okay. We also have this minus sign because the tiles or surface points with a greater phase will irradiate before those with a phase lag. So the resulting locally plane wavefront will have opposite orientation with respect to the total phase gradient nabla Ki. And this expression actually gives you the tangent component of this SR reflection direction. To know also the normal component, we simply impose this relation. So the amplitude of this vector SR must be equal to 1 because it's a unit vector. And with this assumption, we get what we call the generalized law of reflection. So as we can see in this figure in general, we have locally plane wave, so a precise SI incidence direction. This direction lay on a plane, which is the incident plane, and after hitting the RIS surface, the wave is reflected on this along this direction, SR, which belongs in general to a different plane, which is the reflection or radiation plane. And also we will have this angle theta r, which is the angle of the radiated ray with respect to the normal on the radiation plane. Okay, this is different with respect to the case of a regular surface where we have specular reflection, and the specular reflection happens on the same plane as the one for the incident wave, so belongs to the incidence plane. But in general, for RIS, the reflection plane can be different from the incident plane. Okay, anyway, the direction is given by, reflection direction is given by this SR unit vector. Now, I continue with the second order terms in the phase matching relation, which relates the curvature matrix QR of the reflected wave to the incidence curvature matrix. Actually, in this expression, again, we have only a relation between the tangent projections of this matrix. So we have this multiplication of Q with the tangent projection operator P. But we can derive the complete expression of the curvature matrix of the reflected wave by imposing this property I presented you before. So the product of the curvature matrix, reflected curvature matrix, by the direction of the reflected ray must be equal to 0. Of course, SR is computed according to the equation I presented you before, the generalized law of reflection. And with some algebraic manipulation, I skip here for the sake of brevity, we finally get this expression which gives you the curvature matrix QR of the reflected wave, where we have the curvature matrix of the incident wave minus the Hessian matrix of the phase profile Tm imposed by the RIS divided by the wave number. And this expression is multiplied at both sides by this L linear transformation operator. And the expression is given here. It's related again to the radiation direction of the reflected wave SR. Once we have this QR matrix, in practice, it is straightforward to compute the spreading factor of the reflected wave according to the geometrical optics. So that this is the regular expression of the spreading factor for an astigmatic wave, but this ρ1 R and ρ2 R must be computed as the eigenvalues of the reflected curvature matrix, which is computed according to this equation here. So the problem is completely solved because with this expression, I'm able to get the reflected field at any point along the reflected ray. I have in practice to take the incident point, the incident field on the tile. I need to multiply this incident field by the spatial modulation coefficient, and then by the spreading factor at a certain local coordinate S along the ray. And also there is this phase factor along the ray. As an example, I want to show you what happens in the very common case of a transmitting antenna, which emits in general a spherical wave. When we have a spherical wave, in practice, the two principal curvature of the astigmatic wave coincident are the same. We can call them with the symbol S prime. And when this spherical wave hits a RIS, the shape of the wavefront is modified. And this happens also in the simplest possible case, which is the case of a constant phase gradient RIS. Also in the case of a constant phase gradient, when we have a spherical incident wave, the shape is modified, so the radiated wave will not be spherical anymore in general, but will be astigmatic. In fact, if I use this expression and I compute the eigenvalues, I get these two values. So in the radiation plane, the curvature ρ1 R is different from the original curvature S prime because it's multiplied by this factor, cosine of the radiation angle with respect to the normal to the square, divided cosine of the incident angle to the square. While the second curvature remains the same, is not changed. So the curvature perpendicular to the radiation plane is not modified by the RIS. So in the end, this is an astigmatic wave because these two values are different. I also want to highlight that in the case of a constant phase gradient RIS, this term is involving the Hessian matrix of the phase profile will be equal to 0 because there is a constant phase gradient. But still, the curvature matrix of the reflected wave will be different with respect to the curvature matrix of the incident wave because of this operator L. So in the end, after anomalous reflection, the wave becomes astigmatic. Now, I want you to present the last part of the model, which is related to diffraction. We have defined how the RIS modified the reflection, but since a RIS has a finite size, we will have some effect caused by edges. So the radiated field will be influenced also by diffraction on the edges. So in the case it's a rectangular slab, we will have diffraction from 4 edges. And in order to take into account this effect in the ray model, we rely on the uniform geometrical theory of diffraction. So it is based on seminal works by Keller and Kujumijan and Patak, and it is nowadays a very popular approach. So most implementation of diffraction in ray tracing or ray launching tools are based on this geometrical theory of diffraction, where the diffracted field is modeled according to a ray-based approach. According to UTD, the diffracted field can be expressed as a set of diffracted rays, and those rays lay on the lateral surface of a cone, also called the Keller's cone. And the aperture of this cone, beta, is equal to the angle formed by the incidence direction and the edge. So beta equal to beta prime. This law is also called the Keller's diffraction law, and it is a direct consequence of the Fermat's principle. Another interesting thing is the expression of the diffracted field along each of the diffracted ray on the Keller's cone. The diffracted field is expressed by the incident field on the edge multiplied by this matrix coefficient, dyadic coefficient D, and by the spreading factor of diffraction and by the phase factor along the ray. The diffraction dyadic contains the UTD diffraction coefficient that I will explain later, while the spreading factor in this case has only one curvature, which is rho d. This happens because, according to the GTD, the diffracted wave is astigmatic, but one caustic is coincident with the edge. This means that we have one curvature, while the other one is equal to 0. The other curvature radius is equal to 0 on the edge, and when we move away from the edge is simply equal to s, to the coordinate along the ray, while the other curvature, when we move along the ray, becomes rho d plus s. The second curvature, rho d, is in practice the curvature of the incident wave on the plane containing the edge. So in the end, this is the expression of the spreading factor for diffraction. More details can be found in the paper, famous paper by Kujumi Janepatak on proceedings of IEEE. Concerning the diffraction coefficient, this can be expressed in this way, in a dyadic form. And this dyadic is diagonal if we use a proper reference system integral with the ray, incident and diffracted ray. In particular, we can define the incident plane, which is the plane containing the incident ray and the edge, and the diffraction plane. So it is the plane containing each of the diffracted ray along the Keller cone and the edge. If we define these unit vectors phi and beta, which are parallel and orthogonal to the plane, we can define the coefficient this way. So the dyadic is the diagonal matrix, and the components of this diagonal matrix, ds and dh, are called hard and soft diffraction coefficients. The hard are the coefficient along the direction perpendicular to the incidence and diffraction planes, while the soft coefficient apply to the unit vectors beta and beta prime. And this is the definition of the dyadic. And another important thing is the concept of shadow boundary. Basically, diffraction needs to ensure that there is a smooth transition between the illumination region and the shadow region. So this is the incident ray, and if we follow the ray outside of the edge, we have this shadow boundary called incident shadow boundary, ISB, and this is the shadow region, and due to diffraction we have a smooth transition from the when the incident field ceases to exist, we have the diffracted field that compensates for it, and we have a smooth transition. The same happens for reflection. So we have specular reflection, and when we approach the edge at a certain point, the reflection disappears, and when we go beyond this direction, called reflection shadow boundary, RSB, again the diffraction compensates for this transition, and we have a smooth behavior of the field. And this is the expression of the diffraction coefficient that ensure this smooth transition. And in the coefficient, we can see this angle phi and phi prime. Those angles are angles measured on a transverse plane with respect to the edge. We take one of the walls forming the edge as a reference, and we simply measure the angle formed by the incident and the diffracted ray, respectively. The angle formed by the incident ray with respect to the reference wall is phi prime. The one formed by the diffracted ray is phi. So those two angles are contained inside the diffraction coefficients. And also in the diffraction coefficient, we have this Fresnel transition function that ensure smooth transition across the shadow boundary, so that we don't have singularities on the shadow boundaries. And this is the trend, the behavior of the diffraction coefficient for different diffraction angles phi. And we have in the coefficient two terms. The first one, which is called di, is the one that compensates for the incident shadow boundary, the ISB, while the second one is the one that compensates for reflection. And the two are separated by a minus or a plus sign, depending on whether the coefficient is a soft or hard diffraction coefficient. This theory is applied usually to the case of perfectly electrically conductors, PEC, but in recent works, it has been heuristically modified, for example, to model diffraction for other kind of materials, like dielectric materials. There are several proposals, papers that propose this heuristic modification, and our aim is to do the same for RIS, in the case of metasurfaces or reconfigurable intelligent surfaces. Okay, so the procedure we follow for diffraction is basically the same we adopted for reflection. So we repeat the procedure to ensure the phase matching between the diffracted and incident field on the edge, taking also into account the phase modulation imposed by the RIS. We again use the Taylor series expansion of the phases. We substitute in this expression, and from the first order terms, we get this modified law of diffraction, which we call the generalized law of diffraction. So according to the classic UTD theory, the aperture of the Keller cone beta is equal to the aperture of is equal to the incident angle on the edge, beta prime. In our case, the two angles are different. So we have this relation, cos beta is equal to cos beta prime minus the derivative of the phase profile imposed by the RIS along the edge divided by the wave number. So in the end, we have an anomalous Keller's cone with aperture which is different in this case from the incidence angle beta prime. Moreover, along this anomalous Keller's cone, as the RIS in general has an anomalous reflection, we will have an anomalous reflection shadow boundary. This happens why, once again, I repeat that diffraction must compensate for reflection to ensure a smooth transition of the radiated field. And in this case, since the RIS is modulated, we have this spatial modulation coefficient, we have a anomalous reflection that must be compensated by anomalous diffraction. Moreover, diffraction must also compensate for the incident field, and basically the field along the direction of the incident ray. And since this incident field is not modified by the RIS, differently from reflection, which is anomalous, this means that in addition to the anomalous Keller's cone and to the anomalous RSB, we also have the ordinary Keller's cone and the regular ISB, incident shadow boundary. So the two cones coexist. Both must be present to compensate either for the direct ray or the reflected ray. This is one of the main findings of our recent paper. The detailed on this model, especially for diffraction, can be found in the paper. And one more thing I want to add is that applying the phase matching on the edge, and by considering the second order term of the equations, we also get the spreading factor of the diffraction. This is straightforward. In this case, we don't need to consider the whole curvature matrix of the diffracted ray, because we have only one curvature radius, rho d, so we can directly find the expression of this curvature radius, rho d, and it is the following one. So the reciprocal of the curvature radius, rho d, is equal to the reciprocal of the incidence curvature radius on the plane, on the incidence plane, multiplied by this ratio, sinus of beta prime to the square divided by sinus of beta to the square, minus this term, which is related to the second order derivative of the phase profile along the edge. The last part of the paper is the heuristic modification of the diffraction coefficients contained in this dyadic D. In our case, as I said before, we have two different cones, the ordinary Keller's cone and the anomalous Keller's cone. So differently from the classical UTD theory, the UTD diffraction coefficient, heuristically modified, is split into two parts, two different dyadics, which we call di and dr. The second one, the dr, must compensate for anomalous reflection. That's why we have in the expression of the dyadic the spatial modulation coefficient gamma. So in the end, I don't go into the details, but we derived the final expressions of the coefficients for both the regular diffraction on the ordinary Keller's cone and the anomalous diffraction on the anomalous Keller's cone. I want to now to conclude the webinar with some examples. So we implemented the model into a MATLAB tool. And as a first benchmark, we considered the case of a perfect anomalous reflector, which is able to convert a normal incident wave into a radiated wave forming an angle of 60 degrees with respect to the normal of the RIS. So we can see in this plot that the RIS has a size of 7 by 7 square meters. It is centered at the origin of a XY reference system. It's laying on the XY plane. And we considered as a benchmark a grid of receivers placed on the XZ plane at different distances, and we computed the radiated field by dividing the RIS into tiles, and by computing for each tile the reflected field for each receiver of the grid. And we did the same for the border tiles, those tiles on the laying on the edges of the RIS, and for the border tiles we computed also the diffracted field, and we summed coherently the reflected and the diffracted field. The plot shows the distribution of the radiated field. In this case, we normalized the incident field to 1 volt per meter. The frequency was 3.5 gigahertz. And the configuration of the RIS was this one, basically constant phase gradient along the x-axis. So from the figure, we can clearly see the reflection cone centered along the direction theta equal to 60 degrees with respect to the normal. And we can see all these fringes, which are clearly caused by diffraction. So diffraction is really needed to reproduce in a realistic way the behavior of the radiated field. And the interesting thing is that this figure has a very high resolution. So basically, we considered 1.2 million of receiver on this square grid to get image with 1.2 megapixels of resolution. And the computation time in this case, despite the very large set of receiver, if is of the order of tens of seconds, and it might be improved if we parallelize the computation on the different tiles of the RIS, while computing the same result with other methods will need a much higher computation time. It would be unfeasible in practice using full wave simulation. One possible approach, different approach, could be using the physical optics, integral methods, but still to obtain the same result with the physical optics, integral, it would take quite long time, about 18 hours. Actually, we did this simulation using the physical optics method, which is this one. We compute basically a radiation integral, which contains equivalent surface currents, electric and magnetic, J and M, and these J and M currents can be easily computed once we know the incident magnetic and electric field and the spatial modulation coefficient. And actually our result obtained with the ray model, macroscopic ray model, is very similar to the one obtained with the physical optics integral. Actually, geometrical optics can be seen as an asymptotic approximation of physical optics, and this explains why the results are really very similar. On the whole, considering the whole grid, the root mean square distance between the ray model and the physical optics model is 2.1% of the unit incident field. And if we, just to have a more detailed comparison, if we sample the radiated field along this green dotted line, and we compare it with the physical optics one, we get this plot where the physical optics model is the one in red and the proposed ray model is the black line. We can clearly see that the trend is the same and the two lines are nearly coincident, except for a few points. In particular, in this point here, we can see a small deviation, and this is due to the fact that at the moment in the proposed ray model, we miss the vertex diffraction. We only consider diffraction from the edges. Another benchmark example is the comparison between the proposed macroscopic ray model and full wave simulations. In particular, in this case, we considered periodic RIS with parasitic radiation modes, with deflocates modes. And we simulated this periodic structure using the FEM solver of the software CST Microwave Studio. And the RIS was modeled as a reactive periodic impedance sheet with a period D that it's designed in order to ensure a desired radiation direction at theta r equal to 60 degrees when the incidence is normal to the surface. So the relation between the incident and desired radiation angles and the wavelength and the period of the impedance modulation is given by this equation. In our case, the frequency was again 3.5 gigahertz, and the size of the period was 98.91 millimeters to ensure this 60-degree radiation direction. And also the size of the RIS, the RIS was 7 times by 7 times the period D. And if we simulate this kind of structure with this periodical impedance modulation, we get this result. So basically, we have 3 radiation mode. One is the desired radiation mode. The other one is the parasitic radiation mode at -60. So basically, on the other side of the radiation plane with respect to the normal. And the third one is the specular reflection. So we also have a specularly reflected mode, which is also called the zero mode. And we compared the full wave simulation, which is in this figure, the one represented with the red dashed line, with the simulation using our ray model. Of course, as I said, in order to apply our ray model, we had to do 3 simulations, 3 different simulations, one for each of the 3 propagating radiation modes. So the desired one, the specularly reflected, and the opposite radiation mode at -60. And the result is shown in this plot. You can see again that the agreement between the proposed macroscopic ray model and the full wave simulation is really very good, except a small deviation we have in this case for the radiation mode at -60. Anyway, the deviation is quite small. In the end, overall, the overall error on all the points on all the receivers are the overall error is 1.9% of the unit incident field. In this case, the radiated field was sampled along an arch with radius 1 meter, so at a distance of 1 meter from the center of the surface. So we are clearly in the near field, very close to the surface. And the result is even better if we consider higher distances from the RIS. So in the end, the model is quite accurate. And the only problem is that, as I said, we have some small deviation caused by the fact that we don't consider vertex diffraction and also the effect of surface waves. And also another limitation of the model is the one, the usual limitation of geometrical optics. So we are not able to compute the accurate value of the field on acoustic or on foci. Anyway, I'm showing here another benchmark example, which is the case of focalizing reflector. In this case, we placed focus point at a distance of 10 meters from the RIS. So we configured the RIS with this phase profile here, which ensures that the radiated field is focalized in this point 0, 0, 10. The RIS is centered in the origin of the reference system, so the focus point is along the z-axis at a distance of 10 meters. And in this case, the ray model is able to compute the field everywhere except the exact point of where the focus point is placed. Anyway, if we stay at a reasonable distance from the focus, still the prediction of the ray model is quite accurate. Of course, when we approach the focus, we have a singularity, so the field starts diverging. The predicted field by the ray model is not reliable anymore. These plots, for example, shows you the comparison between the prediction of physical optics method, the red dashed line, and the prediction of the ray model. As we can see, the prediction still is quite accurate if we stay at a distance of at least minus 5 lambda, where lambda is the wavelength. So at least 5 times the wavelength. When we go beyond and we approach the focus, the predicted field by the ray model starts diverging, so it's not reliable anymore. Anyway, this is a very common limitation of geometrical optics, and future work will investigate the possible way to deal with this problem and to extrapolate some value of the radiated field on the caustics, which makes sense, is not unreliable, and as it happens currently. Anyway, the one of the most important finding is that except for these very particular cases, the accuracy of the proposed fully ray-based macroscopic model is very good, and also the computational efficiency is much better with respect to other methods, either integral or numerical methods. So our aim is to completely integrate this macroscopic ray model in a ray tracing tool in order to use it, for example, for planning of RIS in a given propagation environment. In particular, one possible application could be to find the optimal placing, deployment, and configuration of one or more RIS in a given propagation environment, either outdoor or indoor. This will be done in future works, as well as possible improvements of the proposed ray model, including vertex diffraction, singularities in the caustics, and extension of the model to the transmissive Hall space. At the moment, the proposed model only covers reflective intelligent surfaces, but it will be extended in the future to transmissive intelligent surfaces. And with this, I conclude my talk and the webinar. I thank you very much for your attention.